We are very pleased to welcome today's seminar presenter, Austin Garren. Austin is a PhD student at the Virginia Tech Department of Forest Resources and Environmental Conservation. He works with Professor Chad Bolding as part of the Mass Bio project, and he's studying forest biomass harvesting operations. Austin, welcome. We look forward to hearing from you at today's seminar.
Okay, great. Thank you very much. Let me share my screen. Okay, can you see that?
Yep, looks good.
Okay. So as you said, my name is Austin Garren. I'm working with Dr. Chad Bolding. I'm a PhD candidate at Virginia Tech, and I'm going to talk about logging residue utilization for bioenergy today. So as we all know, recently there's been an increase in interest in renewable energy, and this is due to several factors, environmental concern, fluctuating prices of conventional sources of energy, and governmental incentives, policy changes, and things like that. But some projections indicate that renewables will supply the majority of electricity in the US by 2050. And woody biomass currently contributes 40.5% of the total renewable energy produced by the US. And so it follows the increase in demand for renewable energy will lead to an increase in demand for woody biomass. So just generally, why would we want to use woody biomass? This provides a renewable energy source that is immediately available, that can be used as a stepping stone for transitions into other types of renewable energy, if not further into the future. And it currently plays a very important role in many states and countries' efforts towards carbon neutrality. It's widely available with potential for growth. There's utilization of waste material. In this presentation, we're talking about logging residues specifically, which are normally on a conventional site, they're wasted. So it utilizes this waste material and provides additional revenue for loggers. And it provides many other benefits that we'll go over later, including landowner satisfaction, easier site procurement, timber procurement, and site prep savings. It can make additional silvicultural treatments viable that may not otherwise be. It can, fuel reduction operations can become viable, which reduce wildfire risk, which is a very important topic right now. And the systems and equipment to harvest woody biomass or logging residues are commonly already in place with the addition of a chipper or a grinder. So there's several different sources of woody biomass. As I said, today we're talking about logging residues specifically. These residues are produced on just about all logging jobs, but there's also waste from mills, silvicultural treatments, as I spoke of, including pre-commercial thinnings, fuel reduction treatments, and energy wood plantations specifically for energy wood production. But as far as residues are concerned, what we're talking about are basically any wood that comes off of a conventional logging site that can't be used for a higher value product. So this includes limbs, tops, small diameter stems, poor quality stems, hardwood crowns, all of that, depending on markets and what's available at the time, can be chipped and used for woody biomass. So just to get some terminology straight to begin with, clean versus dirty chips, that's some terminology you'll hear. Clean chips are used for pulp, so that's not really what we're talking about. These are more uniform in size, uniform in species, have minimal bark and leaves and contaminants, and often roundwood stems or higher value stems are used to make this product because it's a higher value product. But what we're talking about with logging residues and what's used for bioenergy are dirty chips or whole tree chips or fuel chips. They have many different names, but basically they are less consistent in size, They contain basically whatever is put into the chipper. So bark, leaves, branches, everything goes into this. It's often mixes of species, kind of whatever's available. And then grinders produce what's known as hog fuel or boiler fuel. And this is, again, what a grinder produces. And you can think of this as kind of like mulch. That's what's used to create mulch. But it's kind of it's a ground up stringy product instead of a chip. And it often contains more impurities than dirty chips do. So here's like a visual comparison. On the left, we have clean or pulp chips. In the middle, we have dirty chips or biomass fuel chips. And then on the right, we have hog fuel, which is what's produced from grinders. And then a comparison of the machinery that's used to produce these products. So on the left is a clean chipper. You can see hanging down inside of that drum, or the inside of the chipper there, you can see chains hanging down. This debarks the stem as it goes in and produces that clean product. Whereas on the right, this is a whole tree chipper. The stem is fed in the back end there, and it doesn't contain those chains that flail. So the stem goes straight into the chipper, and all the bark and leaves and everything are chipped. Pellets are another form that you'll see, but these are more commonly exported, especially to European countries. And often different products are used to produce this. So roundwood, often higher value stems are used to produce this, but mill residues and logging residues are also utilized for this product. But basically, pellets are made because, like as I said, they're commonly exported. So as we know, wood is 50% water, and you don't want to ship 50% water across the ocean. You'd like to ship as much wood as you could. So pelletizing this basically removes the water content, and they have a similar energy density as coal, but it makes it more efficient to transport and feed into facilities across seas. And but when we're talking about within the US, fuel chips and hog fuel are more common for bioenergy production. So as far as energy wood harvesting methods, there are kind of two different ways to do this. Two-pass methods are more uncommon, and there's kind of three different variations of this. So you can remove the energy wood after the round wood has been removed, but this results in stems being knocked down, tangled, broken, and hard to pick up and collect. You can remove the energy wood before the round wood, and in this case, the felling machine has to work around the standing roundwood stems, which often damages roundwood and makes felling inefficient. And then in this case, if you think about it, the limbs and tops of the roundwood are not able to be used because the energy wood harvesting operation takes place before the roundwood harvesting operation. So you miss out on the limbs and tops that could be chipped in that case. And then specialized equipment can be utilized with either of these first two methods. But this isn't ideal because there's additional moving costs, lower utilization rates of that equipment because it's so specialized, extra costs associated with just an additional piece of equipment. So sometimes you'll see some specialized machines on the landings, but overall it's pretty uncommon. As I said, it's more expensive. This method is more expensive and less efficient, but it can improve chipper and grinder utilization rates, which is a problem often on these operations. But the main way is one pass or integrated harvest. So this is generally favored because of lower costs and higher productivity. So energy wood and roundwood stems are harvested at the same time. And there's kind of two variations on this. These stems can be sorted by the felling machine into piles and then skidded separately, or the felling machine can put all of the stems into bunches and be skidded together and then separated by the loader at the landing. But this results in higher feller buncher productivity because the travel time between stems is reduced. Everything's being harvested at once, so there's no travel between energy wood and roundwood stems. And the feller buncher doesn't have to avoid residual stems, and there's no additional steps required. As far as equipment used to harvest energy wood, it varies according to region. So conventional harvesting equipments vary according to region. And as we just said, most of these energy wood harvesting operations are integrated into conventional operations. So whatever is used in that area is what is used to produce energy wood. So in the Southeast, this is often rubber tired feller bunchers, grapple skidders, trailer mounted loaders, etc. And in the lake stakes, for instance, cut to length equipment is common. So this is used for energy wood production up there. And but other than this, variation also exists due to topography. So specifically in Virginia, because that's the area I'm familiar with, variation exists due to topography. We have mountains and Piedmont and coastal plain in Virginia. So in the mountains, often you'll see tracked feller bunchers, which is what's in the picture there, for the steep ground, and or shovel logging equipment sometimes is used. This is also used in extremely wet areas, swamp logging operations and such. So, but basically whatever's already there is what's used to produce energy wood. Adding additional equipment, as I said, drives up the cost and sometimes can hurt productivity. So trucking is kind of the way chips are transported, basically. Chip vans can often be a problem on smaller landings. That's a chip van in the picture there. This is especially problematic on mountain sites because mountain sites are kind of tight and cramped to begin with. So these trailers are less maneuverable than a lot of log trailers are. And they have considerable off tracking, which is where the trailer kind of lags behind and gets off track in a curve behind the truck. So it makes it harder to get these onto tighter mountain spots or other small landings. But there's not many options as far as this goes, since it's chipped or comminuted in some way. There's no logs there to have any structural integrity, so it has to be some sort of container. But they have top and rear loading trailers, and then have these vents at the top that help for the dumping. So as far as comminution, this is the process to increase density and uniformity of energy wood to facilitate efficient transportation and handling. So chippers and grinders are the two options generally. Chippers use sharp knives that cut the wood into chips. This produces a cleaner product of more uniform size and quality. It can meet higher, more stringent requirements, and in some cases can bring a higher price. They're generally more productive than grinders as well, but in the case of severely contaminated wood, chipper knives are susceptible. So it dulls the knives, and then this leads the chipper to become less efficient, productive, and reduces the chip quality and consistency. But overall, chippers are generally preferred, especially in the Southeast. So this is some examples of chippers, whole tree chippers. And as you can see in the diagram there, they have knives which spin on a disc or a drum. In this case, it's a drum. And these knives chip the wood up. Grinders tend to be less productive than chippers and require more energy to operate. This makes them less efficient. It provides a coarse final product that can't be used in some facilities and creates excessive ash when compared to chips. So as I said, not as common as chippers, but they do have a few advantages in certain situations. So since they use blunt tools to crush the wood instead of cutting, they're often better for more contaminated wood, such as wood that's been pushed up in piles or whatever and has been contaminated with dirt or rocks. It doesn't dull. Those tools are already blunt, so it doesn't dull the tools. And so if you think about a large scale post-harvest residue recovery operation or something like that, they're good for that. And then mulch, they're used to produce mulch. So this is some examples of grinders. On the top, we have a horizontal grinder, and the bottom, we have a tub grinder. And then that on the right, you can see the blunt tools used to just kind of crush and tear up the wood. So just to give an idea of kind of a typical biomass harvesting operation in the southeastern US, as I said, varies by region. So this is kind of what we see around where we are. So this is kind of, especially in the mountains, what a conventional site may look like that's not used for biomass. So there's lots of residues left on the site. You can see, limbs, tops. You can see a larger stem at the bottom there that's probably not good for anything else besides, pulp or biomass. So this is the material we're talking about. This material is harvested by a feller buncher, usually of some kind. So in the mountains, we have tracked feller bunchers often, as you can see on the left. And on the top there, the top left, that's a shovel with a bar, chainsaw bar grapple attachment. That's less common, but I saw that on one of the sites I visited over the summer. And then in the Piedmont or coastal plain, you'll have rubber tired feller bunchers as seen on the right there. This is transported to the landing by grapple skidders most often. Rubber tired grapple skidders are kind of common regardless of region. And then on the landing, you'll have a loader, knuckle boom loader in the case of a southeast operation. There can be one or two loaders depending on how the operation is set up, but the skidder brings the material to the landing, and then that's also where the chipper sits. This video just kind of shows this process. So you see the loader is feeding that stem into the chipper. You can see the skidder coming up behind it and pulling material to the loader. And then the chipper chips up that material and blows it into a chip van. And then trucks are used to transport the material from the site. And those are really the most common way, especially in the Southeast, to get the material to the mill. So that's kind of a typical operation. But the problems arise with these operations. A lot of the problems have to do with thin profit margins, with net losses common. Because if you think about this, this material is wasted on a lot of sites. So it's basically the lowest value product on the site, and it requires an additional step to process, which costs money. So these operations struggle with profitability a lot. There's many factors that affect this: equipment type and size, the amount of capital they have invested, low chipper and grinder utilization rates. As I said, these machines often sit on the landing even if they're not being used, and often they're not used continuously. So they have low utilization rates. And then trucking availability and productivity is often a problem, as with any other conventional logging operation as well. This video on the left, you can see this is what a logger sent to me over the summer of 2020. And in this case, he was only able to stay running that summer because he had a land clearing contract. But they had no market for the chips during COVID at that point. So he was literally just blowing these chips out on the ground. And they were able to do that because the landowner just needed the land cleared, but obviously that's not ideal. So another common problem that's talked about a lot concerning environmental impacts, concerns specific to energy wood harvest deal with the amount of residual downwoody debris left. That's really the only difference between a conventional and an energy wood operation. So the common concern is nutrient depletion. If we remove all the biomass from a site, then it can hurt future productivity theoretically. This is rarely observed in practice, but this could be just because the observation periods aren't long enough to observe this. Either way, it can be remedied with fertilization, but this adds costs and other environmental concerns. Some more environmental impacts having to do with the residues. If the residues are gone, they can't be used for erosion control. They're often used for best management practices or BMPs, which help control erosion. Seed and mulch can be used, but that adds costs. This material is already on the site, so seed and mulch they have to buy. Another concern is less woody debris for brush mats, which are a method of reducing, or not reducing, but reducing the potential for compaction from machines, especially in cut to length operations. There may be less downwoody debris for other BMPs, such as closeout procedures, which help limit unauthorized access. Barrett et al. There compared this and observed no significant differences. We'll talk about that a little bit later. And then also there's questions of whether current BMPs are applicable or sufficient for energy wood harvest because they were created for conventional harvest. So typically, BMPs are effective on conventional sites when installed correctly and in appropriate quantities. And since operations are normally integrated, then BMPs should be effective on energy wood harvest. A lot of people have theorized that, but there's few studies that actually quantify that. And then Evans et al. There suggests that additional guidelines should focus on downwoody debris retention, since this is the main difference. And then kind of the third thing that my research kind of looks at is the characteristics and stakeholder outlooks. So surveys that do this are common on conventional operations, but less common on biomass operations. But they are useful for stakeholders in the industry to kind of know what a typical operation looks like and kind of know, statistics about them. It's good to be able to characterize these operations to support decision making. So Barrett et al. There surveyed loggers in the Piedmont of Virginia and found wide range of production levels, most integrated energy wood harvesting with roundwood. Most businesses had produced at that time biomass for an average of 6.8 years. Most used large chippers with an average age of 12.5 years, which meant they were often used chippers. Owners were more likely to respond they profited if they had less of an investment, such as purchasing used chippers. And then common reasons for harvesting energy wood was increased landowner satisfaction, and most loggers viewed energy wood harvesting positively and plan to continue. Other studies have been conducted in other regions, and this varies by region. So really we need regional studies showing this that can be compared. So this is kind of where my project comes in. So this is the title of my dissertation, Evaluating Energy Wood Harvesting Operations in the Lower Mid-Atlantic region of the US. So my first chapter evaluates the productivity and costs of 5 energy wood harvesting operations in the Lower Mid-Atlantic. So our objectives were to determine the harvesting productivity and costs of select energy wood harvesting contractors, evaluate commonly used methods, and evaluate the efficiency of these practices. So the study design, we had 5 basically case studies that we looked at due to budget and time constraints. And we had 2 mountain sites and 3 Piedmont and coastal plain sites to capture the variation observed in our region. So we have mountains, Piedmont, coastal plain within the lower mid-Atlantic, which all have different species and different terrains and climates and such. So the splitting the sites allowed us to capture that variation. And then we analyzed on the site level and then just drew comparisons between the sites. Additionally, each logger was interviewed using a set of questions to gain insight into what we saw when we observed their operations. Methods, we use video cameras on the landing to record the activities there so that we could be collecting data on other parts of the operation. Activity sampling was conducted for utilization rates for machines on the landing. Time motion data and on the other harvesting functions, not on the landing, were collected in the field, and as well as timber inventory to know what was on the site. And then cost per ton was estimated using the machine rate method and Auburn Harvest Analyzer, with assumptions being gathered from the most recent literature. So just a quick look at the results as far as productivity. These sites kind of showed the negative effects that quotas, various things that commonly happen on these operations have on productivity. So various sites that we observed had quotas or down machines or unbalanced equipment mixes or small landings, truck shortages. So this kind of documented all of those problems on productivity. Generally, machines were less productive when handling energy wood than round wood, and this is just due to the smaller average diameter of the stems. Mountain feller bunchers, on the other hand, were able to achieve a higher productivity because of the larger average size of the stems. Though loader capacity, is often not the limiting factor, at least in this case. Two loaders were often used, particularly within the coastal plain. This could be due to just convenience. It kind of makes sense intuitively to have, one loader for biomass, one for roundwood. This could also have effects on the amount of room for sorts or inventory for other products, because there's more products coming off of sites in the coastal plain, or it can also help facilitate efficient trucking. But mountain operations tended to have one loader, whereas coastal plains operations had two. But trucking was highlighted as a very common problem, just as with any other harvesting operation right now. It's very expensive, and there's little room for increased productivity in this area. So anything that can be done to facilitate more efficient trucking would be good. So this is a table showing the costs that we estimated. So Site 1 had favorable stand conditions, no quotas, relatively normal production rate. And so this was kind of a normal coastal plain site. I should mention that the first 3 sites, 1 through 3, were coastal plain operations, and then 4 and 5 were the 2 mountain operations. So as I said, this was a normal coastal plain operation. They had a cut and haul rate of 26.18 a ton per metric ton. And we came up with a balanced theoretical cost for each one of these sites, where we balanced the amount of machinery on the site. And theoretically, they could have achieved a cost of $23.89 a ton. Site number 2 was the most productive, but had a higher cost, and this was due to the large number of machines present. And this was because of COVID. So the operator in this case wanted to keep his crews busy, and so there were actually 2 full crews on the site at the same time. So it raised costs. There was just kind of an unnecessary amount of people and equipment there. But we came up with a balanced cost of $30.87 a ton compared to $31.95 observed. So not a whole lot better, but this was, again, just due to the large amount of machines present. Site number 3 was kind of the most abnormal coastal plain operation we observed. So you can see the cut and haul rate there of 38.28 per ton. This is not good. At the time, they were under heavy quota restrictions, and by the end of the week, they actually, both mills within the area that they supplied had cut them off. They were not taking energy wood anymore. And the site they were on was actually almost completely energy wood. So really, they kind of shut them down while we were there. So this resulted in this abnormally high cost. But theoretically, with a balanced cost, we estimated a cost of $25.29 a ton, which is comparable to the first site there. Site number 4 was the first mountain operation. it was kind of like site number 1 in the coastal plain, no quotas, kind of a normal operation for them. They had similar cost as the site 1, and really the only problem on this one was limited space at the landing. So there was various bottlenecks at different points in time that slowed them down. But this one could theoretically achieve a cost of $22.61 a ton, which was the cheapest theoretical cost we came up with. And then site number 5 there was the more expensive mountain operation, and this was due to an additional machine in the felling function. So they actually had the same tracked feller buncher as site number 4, but they had that shovel that I showed in the picture. They had that machine there as well, and they used it to kind of pre-bunch before the skidders picked up the wood. And they felt it was necessary, but the operator on site number 4 was able to do that with the feller buncher and didn't have that added machine cost. Additionally, on this site, they were skidding. It was a bad location. There wasn't a good road to the bottom of the site, so they were skidding about a mile uphill, which led to about 20-minute turn times. So just a kind of unideal situation on that site. But we came up with a balance cost of $28.66 a ton for that operation. But kind of the last moral of the story here is the hauling function you can see. So all 5 sites achieved an average of onboard costs, which is harvested onto the truck, of about $20 a ton. But then by the time you add the hauling costs in, that adds about $12 a ton or more. So hauling is the most expensive function by far, and is a big problem for loggers right now. So second chapter of my dissertation addresses the environmental impacts. So best management practices, estimated erosion, residual down woody debris, and ground cover characteristics following biomass and conventional harvest. So, and this was in the mountains of Virginia, the second chapter was. So again, our objectives were to estimate potential erosion for the operational features, quantify the feature areas, determine BMP implementation rates, correlate BMP implementation scores with estimated erosion rates, and quantify the size, class, composition, and masses of residual ground cover and woody debris. So we wanted to address these questions, biomass, basically see if there was a difference between biomass and conventional harvests in Virginia. So we did this by comparing 10 biomass and 10 conventional sites in the mountains of Virginia. And this kind of went along with the previous study I had mentioned earlier by Barrett et al. 2016, did a similar study in the Piedmont region of Virginia. So similar methods were used. Erosion was estimated using USLA forest. And then the sampling method was adapted from the Christopher and Visser there in the prior paper that I mentioned. But basically we were able to come up with a weighted average erosion rate for the site based off of the areas of each of the operational categories on the site, such as skid trails, haul roads, stream crossings, SMZs, streamside management zones. So BMPs were evaluated on each site using the Virginia BMP audit. Visual ground cover was estimated using methods from the previous paper. Residual woody debris was estimated using Brown's transects. And then for data analysis, Mann-Whitney tests were used to test the null hypothesis that there was no difference between biomass and conventional sites for these various parameters of interest. Chi-square tests were used for differences in slash use, and then regression was used. A simple linear regression was used to predict weighted average erosion rates from BMP implementation rates to see the relationship between the two. So kind of the only thing to see here is the roads category there. There was a significant difference in estimated erosion between biomass and conventional sites. Biomass sites were significantly more erosive, but these erosion rates for haul roads in the mountains are actually low compared to other studies, both of them. So though there was a significant difference in the two, they're both still lower than other studies that have estimated erosion on haul roads in the mountains. But this is percent of total erosion from each category. And you can see skid trails here. There was a significant difference between biomass and conventional sites for skid trails, with conventional sites having 81.1% of the total erosion that came off of the site, estimated erosion, coming from skid trails, compared to 67% on biomass harvest. And this is significant because skid trails generally make up about 6 to 10% of the site area, yet they make up 67 or 81% of the erosion. And then this is showing kind of the same thing as the first table. This is just erosion mass. Again, there was a difference between biomass and conventional, but these rates were, or these masses were relatively low compared to other studies. BMPs between biomass and conventional were interesting. So biomass sites had significantly higher BMPs for SMZs, which is streamside management zones, skidding, and overall than conventional sites. And the concern with these was, that BMP implementation would be lower on biomass sites. So we found that in some cases, BMPs were actually better on biomass sites than conventional sites. And then ground cover, this was visual ground cover estimated. So the significant difference here was with heavy slash. You can see there was a little bit less heavy slash present on the biomass sites than conventional, which is logical. And then this is downwoody debris, actually estimated tons per acre. So there was a significant difference between biomass and conventional harvests in basically all categories, size class categories over 1/4 inch in diameter. So conventional harvest had significantly more tons per acre of downwoody debris remaining, but there was an average of 10.98 tons per acre remaining even on the biomass sites. So there are still residues available for BMPs on these sites. And then this shows weighted average erosion rate predicted from overall BMP implementation score. And basically what this means is, as you can see, the negative relationship as BMP's implementation is higher, weighted average erosion rates for the site go down, which means that BMPs are doing what they're supposed to, reducing erosion rates, and that they are effective at that. And as you can see, this is for biomass and conventional sites together. The third chapter addresses the characteristics and kind of owner, business owner attitudes regarding energy wood production. So the objectives were to characterize current biomass harvesting operations in Virginia and examine their business owners' current and future outlooks on the harvest of biomass for bioenergy. So methods for this, this also expanded off of a previous study done by Barrett et al. 2014. Biomass loggers across Virginia were surveyed regarding operational characteristics, demographics, perspectives, outlooks, etc. And this was different from the original survey, which just surveyed loggers in the Piedmont of Virginia, so expanded to the entire state and updated this survey. But the list of loggers was obtained from the Virginia Department of Forestry and refined with the help of biomass consuming mills within the state. It was a paper survey, and the methods for this survey instrument were developed using, and the methods for sending it out were using the Taylor design method. And this survey instrument was the same survey instrument from the original survey, and it was just updated for the current survey. It contained Likert scale questions, continuous, categorical, and open-ended. questions. This was approved through the IRB, and data was analyzed using Wilcoxon rank, or Wilcoxon rank sum, Kruskal-Wallis and Steele-Wallace tests for hypothesis tests, and then summary statistics were used to just characterize the operations in general. So this shows average age of respondents, or the distribution of ages. And kind of the moral of the story is, has been documented in many other studies, the logging workforce is aging. So the highest response there was 50 to 59 years, and the second highest was 60 to 69. So, many of these loggers may be considering retirement, which raises concerns for the future of the workforce. But most operations consisted of a single crew with 4 employees, primarily focused on roundwood production. So they were roundwood operations that also produced energy wood. Energy wood was not the focus of their operation. And most loggers were still located within the Piedmont region. Chipper ages, as if you remember, the median chipper age of the other one was 12 point something before. So it's pretty consistent in this study with a median of 13.4 years. They were relatively large again, 650 horsepower median. Single loader was often used with 3 chip vans per crew. And then the average total or the median total investment in biomass production equipment, so this was in absence of the equipment they already had, was $400,000, which was double what it was in the first survey, which makes sense since they've had 10 more years to accumulate more equipment and spend more money on the equipment. This just kind of shows how widely the production levels range. They were kind of all over the board, but biomass made up about 31% of total production on average, and was mostly sourced from loggers' own residues. Very few utilized any residues from other harvesting operations that weren't their own. So reported advantages of biomass production were the top 3 were improved aesthetics, a clean looking site, which helps with increased landowner satisfaction, and it provided an additional market and a source of revenue, which helped the loggers diversify their business. But common barriers to profitable biomass production were low delivered prices received for biomass, unstable markets and demand, and high fuel prices. This table shows at the top reasons for biomass market entry, and then at the bottom there, the impact that the decision to enter the market had on their operation. And these were Likert scale questions, so a scale of 1 to 5, with 5 being most agreeants. And you can see the Wilcoxon sign rank indicates the null hypothesis was that the response was neutral or equal to 3. So the top 3 reasons for beginning production of biomass were to satisfy landowners that wanted their residues chipped, to be competitive on timber sales that required it, and to diversify their business. And then you can see that the connecting letter report there indicates that they were significantly more likely to respond for those reasons. They began production for those reasons, and less so to increase total profit or because a mill encouraged them to do it. And the impact of this decision on their operation. Generally, they agreed that it made their overall business stronger and that it was a good decision, but they also agreed that it made their business more challenging. And if you see the bottom 2 responses there, so least agreeants, they did not agree as much with the statement that on average they make a profit from the biomass that they produce, and that they had never harvested biomass at a financial loss in order to satisfy a landowner. So there are good things about producing biomass and other reasons, but profit kind of, is still kind of hard with biomass. This shows a regional comparison between Piedmont and coastal plain operations. There weren't enough in the mountains to run statistical comparisons, but basically all of this is showing that coastal plain operations tended to be higher production and higher, kind of larger scale in general than Piedmont operations. So they had higher production levels and more employees, more crews, bigger chippers, more loaders, all of that, higher investment. So they were just larger scale in general. And then this was a profit analysis. So just several of the parameters we estimated compared to loggers who agreed with us that they were profitable versus those that were neutral or disagreed they were profitable. And the only relationship we were able to find were that loggers that had produced biomass for longer were more likely to agree that they profited. So it's possible that it just takes longer to profit from biomass production.
Austin, we've got just a couple more minutes left, so if you could wrap things up, that would be great.
Okay. All right. This is my last chapter. Basically, this chapter just took the data from the second chapter and combined it with two other studies that were done in the Piedmont and coastal plain. Same objectives. But in this study, instead of comparing biomass and conventional, that had already been done in the other studies. So this compared biomass sites across the three regions, and then it compared conventional sites across the three regions. So basically this table shows mountain sites were more erosive in general than the other two sites, which makes sense because of their terrain. And then this shows that skid trails, again, had very high erosion rates compared to their area. This figure just, again, exemplifies that between, you can see skid trails had a lot of erosion compared to the other areas. And this is for conventional sites, same relationship. So mountain sites are erosive and road network features are erosive as well. BMPs were implemented at a higher rate on conventional sites or on biomass sites than conventional sites again. And that's pretty well the moral of this story as well. It's inherently harder to have higher BMP implementation in the mountains due to the steep slopes. This shows that BMPs were equally effective at reducing erosion rates on both biomass and conventional sites. And then the p-values on the right show that biomass and conventional sites both had more downwoody debris remaining on conventional sites than biomass, or I'm sorry, mountain and coastal plain operations. There were more downwoody debris on conventional sites, and then there was more downwoody debris remaining on conventional sites in the mountains than there were in the Piedmont. And this suggests that there's just more residues available in the mountains, and this is due to the lack of pulpwood markets in these areas. So just a summary, residue utilization for bioenergy is expensive and it can result in net losses, but there are numerous other benefits that often make it desirable. Biomass harvesting does not result in increased environmental impacts to water quality compared with conventional harvest. Biomass operations often had higher BMP implementation and lower erosion rates. Existing BMPs control erosion on both site types, and mountain operations are inherently more erosive and have lower BMP implementation, so this should be a focus of future BMPs. So those are the resulting manuscripts, and that's kind of all I've got. I defend March 23rd, graduate in May, and we'll be looking for a faculty or postdoc position in the future. So with that, I'll take any questions.
Okay, great. Thanks so much, Austin. We do have one question, quick question here. The question is there a limitation to using forest residues on publicly owned land, such as federal forests, national parks, et cetera, in terms of using that as biomass feedstock? Are there extra limitations there?
I'm not sure, but not that I'm aware of. I haven't heard of any, and I know that at least in this area, they do sometimes produce biomass from residues on public lands as well.
All right, terrific. Well, we are up against the end of our allotted time for the seminar. So as any of you have any follow-up questions, please feel free to contact Austin. I assume that's okay for people to email you if they have any questions or issues they'd like to bring up. Is that all right?
Yes, that's fine.
Okay, terrific. And thank you to all of you for attending. I hope to see you again next week at our next Mass Bio seminar. Thank you.
Thank you.